Okay, this is Professor Lee. So we continue this our discussion on the computer-age statistical inference. It's a great book. It's a great honor that I can study this with you and understand what inference is. Given that our AIs now have a lot of inference models, that I think it's very beneficial for us to have a good foundation of knowledge about what inference is. One of the ways, and it's a very insightful ways to get to the truth. So basically, whatever we do in academic pursuit is we try to get to the truth. So there are different ways, but inference is definitely one of the ways. Now we begin session 2. Okay, session 2. Our CASI, the computer-aided statistical inference, I call it CASI. CASI chapters 2 and 3, and it presents a quarter that began in 1763. 1763, the quarter began. It has never been really settled, and decides what a clinical trial is allowed to conclude. That that the new drug discovery and the verdict that this drug is safe to use is based on a lot of statistical work, inferences as well. So what do you mean? What do we mean by probably? What do we really mean when we say probably? So consider two sentences. This coin has probability of 1/2 of lending heads. This defendant is probably guilty. So both use the same word, but they cannot mean the same thing. The first describes a property of a physical object and its long-run behavior. Flip it forever, and half the flips are the heads, and another halves will be coins. So probability lives in the word. The second describes a state of a mind confronting evidence. Okay, so probability in that sense lives in the observer. Okay, there's no long run in this case. The defendant did it or did it not. Okay, or there's no consequence of repetition in which she did it half the time. Therefore, probability of a people, the event and behavior and their memory and all of that lives in the observer. So frequentism builds the whole of statistics on the first meaning, and Bayesian builds the whole of statistics on the second. Everything that follows, every disagreement about clinical trials, every dispute about what the study proved, descends from that fork. So I want to be clear about the posture that I'm asking for. Afron and Hasty treat both schools as legitimate, and by chapter 15 they use both inside a single procedure. Do not leave this lecture thinking either side won. Okay, so two schools. So start with the frequentism. Judge the procedure, not the case. So the frequentist refuses to assign a probability to a hypothesis. The drug either works or it does not. That is in fact not a chance event. What may be assigned a probability is a behavior of a method. So if I follow this rule forever, how often will it mislead me? So this is why frequentist quantities are so easily misread. A 95% confidence interval does not mean 95% of chance the truth is in this interval. It means instead the recipe that produced this interval captures the truth 95% the time it is used. So it's about the recipe, about the method, and the confidence, level of confidence you can have about the method. An analogy from your own work is good editorial policy is one that applied consistently publishes a few first fruits. This says nothing about whether today's particular article is true. So Afron and Hasty's own framing is that frequentism seeks accuracy through the device of an imagined infinite sequence of repetitions that never actually occurs. Next, unbiasedness, variance, and the idea of fair instrument. So an estimator is an unbiased estimator if across the imagined infinity of repetitions is right on average. It does not systematically rate high or low, a fair scale. Its variance, 분산, is how much it jumps about from one repetition to the next, a precise scale. Classical theory is how much it jumps about from one repetition to the next. That's a variance. Classical theory thought estimators that were unbiased and had the smallest possible variance, the fairest and steadiest instrument variable. So this is frequentist optimality, chapter 2's technical core. Okay, so for a century, this seemed obviously the right goal. Who would prefer a biased instrument? But hold the question in session 5, we meet the James Stein estimator, which is deliberately biased and reliably beats the unbiased one, a result so unwelcome it was called a paradox for years. This is slide 36. We are looking at Bayes' rule. Evidence updates belief. The rule dates from 1763, published posthumously. Inference and Hasty wrote dryly that its early advocates considered it as an argument for the existence of God. So the structure is one any reader of arguments already knows. How you begin with a prior view, evidence arrives, you end with a revised view. So the rule specifies exactly how much revision the evidence warrants. So 3 components: the prior, what you believed before, and the likelihood is how well each hypothesis predicts the evidence you actually saw, and the posterior, what you should believe now. So its enormous advantage is the posterior answers the question people actually ask. So given the scan, what is the probability that I have the disease? So frequentism cannot answer that, Bayes can. However, it's got enormous cost is that you must supply the prior. And where does the prior come from? 37, Bayes' rule as ratio. Odds instead of probability. Odds rather than probability, because odds turn the rule into simple multiplication. So 2 to 1 against times, 3 to 1 in favor gives 3 to 2 in favor. So the likelihood ratio is the evidence of whole contribution. Under hypothesis A, how likely was that observation? Under hypothesis B, and divide. Okay, so notice that what the formula makes visible. Evidence never determines belief by itself, but it multiplies a prior. So 2 honest people with different priors shown identical evidence still disagrees, and Bayes' rule says exactly by how much. Okay, so that's a proposition about intellectual life, not merely about statistics. It's worth defending against both dogmatism and relativism. maybe I am a Bayesian. I never thought that way, but maybe I am. Okay, moving on. So the physicist twins, a physicist's wife is pregnant with twins. The sonogram shows that twins are the same sex. Are they identical or fraternal twins? 일란성 or 일란성 쌍둥이. So the prior comes from a genetics table. Public, reliable, built from millions of previous births. 1/3 of twins are identical, 2/3 are fraternal. So the odds is 2-1 in favor of fraternal. The likelihood is identical twins are always the same sex. Probability 1. Fraternal twins are the same sex half the time. Probability is 1/2. The sonogram, therefore, favors identical by 2-1. Now, multiply 2-1 against times 2-1 in favor equals even odds. So the twins are exactly 50-50 identical or fraternal. Okay. Because the sonogram shows the twins are the same sex. Inference and Hasty's summary. The doctor's odds ratio, prior odds ratio 2-1 in favor of fraternal, is balanced out by the sonogram's likelihood ratio of 2-1 in favor of identical. Canceling out. 39 is the controversial case and why it is rare. So a disease, nobody object to the twins calculation because the prior is not an opinion. It's a frequency drawn from a genuine record. The physicist turns to the page, marks it same sex, and reads off 2 million previous cases. And Efron and Hasty say plainly, when past experience genuinely provides the prior, there is every good reason to use Bayes' rule, and no frequentist would dispute this. The disease affects 1 person in 100. So there's a test which correctly detects it 90% of the time, and which gives a first alarm 10% of the time. You take the test, it comes back positive. What's the probability that now you have the disease? And answer is about 8%. Okay. Here's the arithmetic, and notice that this is trivial. This is not a failure of calculation. Imagine 1,000 people, 10 of them actually have the disease, and the test catches 9 of those. 990 are healthy and test first alarm on about 99 of them. So 108 people receive a positive results. Only 9 of them are ill. So 9 divided by 108 is little over 8%. So the test is accurate. Test is behaving exactly as advertised, but population is overwhelmingly healthy, so the first alarm simply drowned the true ones. So this is called the base rate neglect. It's not an arithmetic failure, it's a failure to remember the prior. So Bayes' rule is the discipline that prevents it, and which is why the school that insists on priors has a genuine claim on our attention. Okay, this is slide 40, a Bayesian versus a frequentist comparison. Now we're gonna walk you through the table row by row. Okay. So the Bayesian probability describes degree of belief in hypothesis. Frequentist, long-run frequency of a procedure's behavior. Bayesian answers the question, given my data, what is likely true? Frequentist question, how often does this method mislead? Bayesian requires a prior distribution, and it got to be supplied by you. And frequentist requires sampling model and hypothetical infinity of repetitions. Bayesian chief virtue is coherence, conditions on the data you actually saw. Frequentist chief virtue is objective, no beliefs required, verifiable guarantees. Bayesian's chief vulnerability, where does the prior come from? Frequentist says nothing about the case in front of you. So verdict of the book is that both schools survive. And later in chapter 15, it will use both at once, and neither school is embarrassed by this. 41, the medical test, where intuition reliably fails. Okay. So let's say a disease affects one person in 100. A test detects it correctly 90% of the time and gives a first alarm 10% of time. You test positive. What is the probability you have the disease? Almost everyone answers about 90%, but correct answer is roughly 8%, right? We looked at before. So work it through with the 10,000 people. 10 actually have the disease, 9 of them test positive, 999 unhealthy, and so on. So a disease affects okay, 108 people test positive and 9 are ill. 9 divided 108 is about 8.3%. So which we called baseline neglect, base rate neglect. So screening. Mass screening for rare conditions generates mostly false positives by mathematical necessity. So whatever the test quality, this is why screening guidelines are contested and why more testing is not automatically better. So security and fraud detection, an algorithm flagging rare events in a large population will produce its list dominated by innocent cases even when it is working exactly as it's designed. Forensic evidence in court, the prosecutor's fallacy is base rate neglect in a week. The probability of this evidence given innocence is not the probability of innocence given this evidence. So any judgment about a person based on a membership in a group, the judgment is based about a person of a group identity. The rarer the trait being inferred, the more the prior dominates and the less the evidence tells you. Okay, so that's the harm of prejudice working. So the pattern to internalize is when the thing you're looking for is rare, even excellent evidence leaves you uncertain. That's a lot happening in the real world right now. Uninformative priors and why ignorance is hard to write down. If the prior is the problem, why not choose one that assumes nothing? Okay. Spread belief evenly across all possibilities and let the data speak. So Eflin and Hasty devote section 3.2 to why this is harder than it sounds. Consider a quantity that could be any length between 1 and 0 meter. Spread belief evenly across lengths. Now consider the same unknown expressed as an area. Evenly spread beliefs about the length is emphatically not evenly spread about the area. So the transformation bunches it up. Two descriptions of the same ignorance disagree. So knowing nothing has no unique mathematical expression. Every flat prior is flat with respect to some particular way of writing the question down, and the choice is commitment. Now, chapter 13 will return with Jeffrey's partial solution. Now, the lesson is philosophical. Neutrality is not a position one can simply occupy. It has to be constructed. Every construction chooses something. There are flaws in the frequentist inference written by Frequentist. Efron and Hasty devote a first section to the weakness of the school they mostly belong to, and it is worth reading as a model of intellectual conduct. So central complaint is this. Frequentist quantities describe the procedure's behavior across an imagined infinity of repetitions, most of which have nothing to do with the data you actually observed. So there are constructed examples where a confidence interval is technically valid and obviously absurd for the data at hand. Cases where you can be certain the interval contains the truth or certain it does not, and the 95% label persists regardless. So Fisher's conditionality principle in session 3 was one attempt to patch this, judged by the circumstances they're actually obtained, and it patches the problem, damages the theory's purity. So neither school is coherent all the way down. Both are useful nearly all the time. That is the mature summary, and it's also the author's own theory. So model the conduct. They criticize their own side hardest. That's difficult. But this is what students should learn from this section, that it is coming from your own group, you have to model the conduct. That's the statistics. Now, questions for session 2. Number 1, if a jury is told a DNA match has a 1 in a million first match rate, what must the jury also know before that number means anything, right? The missing sentence. Number 2, Bayes requires you to state a prior in public and let evidence overturn it. Is that a higher or lower standard than a reflexivity of your own discipline asks for? Number 3, frequentism binds you to a rule set in advance, even when the rule disfavors you today. So where in scholarly life do we already accept such self-binding, and where do we refuse it? Number 4, construct an example in your own field where two careful people shown identical evidence should still disagree, and say how much of the disagreement is prior and how much is a likelihood. Okay, so what you know is summarized in this page again. So frequentist probability. In one sentence, the long-run frequency of a procedure's behavior. The common error is that we tend to apply it to a single case, and they're in real-world events not repeatable. Bayesian probability is a degree of belief revisable by evidence. Common error, forgetting it depends on chosen prior. Confidence interval, an interval from a recipe that captures the truth 95% of time. The common error, 95% chance the truth is in here. No. Prior, posterior is a belief before evidence, belief after, divided by belief after. Common error, treating the prior as optional. Term, likelihood ratio in one sentence is how much better one hypothesis predicted the data than another. The common error, reading it as an odds themselves. Base rate, one sentence, how common the thing is before you test for it. The common error is ignoring it when the condition is rare. Unbiased estimator is a right on average across repetitions. A common error is assuming it is therefore the best. Okay, on priors and the impossibility of reading from nowhere. For now, we see through a glass darkly. Now I know in part. This is Paul's remark from 1 Corinthians 13:12. The latter part is much better. The later will see our Lord Jesus face to face. without the veil. That's a promise. Okay. Now going back to Bayes. Okay, Bayes' rule contains a claim that humanity has arrived at independently and have argued about ever since. That there is no reading from nowhere. Gadamer called it Bururteo, prejudgment, and insisted it was not a defect of interpretation, but its condition. So you cannot approach a text without already expecting something of it. And if you could, you would understand nothing. What Bayes adds to that insight is discipline. The prior must be stated in advance in public in a form that evidence is permitted to overturn. This is far more demanding requirement than acknowledging one's positionality. It is positionality made falsifiable. But notice the frequentist rival virtue, which is also an ancient one. He that swells to his own hurt and changes not. A rule you bind yourself to in advance and follow even on the day it disfavors you. This is method as a discipline of the will rather than that of an intellect. And this is not a lesser thing. So two honest postures, epistemic postures, then state your prior and let it be corrected. Or bind yourself to a rule before you know which way it will cut. A mature researcher, like the mature reader, knows which occasion call for which. So do not stage in favor of either school. All right? That was session 2. Thank you.